The purpose of this screencast is to show you how to calculate energy absorbed or released in a phase change. So the directions for this example problem say draw a heating cooling curve for the following situation, then complete an LOL chart. Finally, calculate how much energy was absorbed or released. So the scenario we're looking at is an ice cube tray full of ice, 235 grams to be exact, allowed to melt completely at 0 degrees Celsius. So one of the important things to recognize here when we're drawing our heating or cooling curve is to first identify what is happening to the temperature. During a phase change, we should not observe a change in temperature because we know that changing phase means that particles are either separating or coming together. So in this case, we're melting. Melting represents the phase change from solid to liquid. So that tells us that energy is being absorbed by the system because those particles need to be moving farther apart from each other. Go from solid particles touching and vibrating to the liquid particles farther apart from each other. So during this phase change, we will see no change in temperature, which means that we're going to have a flat line at 0 degrees Celsius. Take a second to draw your temperature versus time graph, showing that you have a solid melting into a liquid. We also know that if a substance is melting, we are going to be using the heat of fusion to determine the amount of heat required or released during this situation. What we can do is fill out our LOL diagram to confirm that energy is actually being absorbed by the system and not released. When we look at this, we want to fill in our LOL diagram. Our thermal energy for this example is going to be about a block of energy because I would say ice is pretty cold. We also want to include 1 block of phase energy because we represent solid phases with 1 block, and we have been getting in the habit of including 1 block of chemical energy. Even though we haven't really talked about it, we know it's present, so we will include that. The system here is our ice that's melting, and after it melts, we know that its temperature has not changed throughout that whole melting process. So our thermal energy has not changed. Temperature is a representation of thermal energy. Our phase energy, however, did change. We went from a solid to liquid state of matter. And we're not describing a chemical change here, so we're going to maintain 1 block for our chemical energy. What this shows us is that from our initial conditions to our final conditions, we have increased by 1 block of energy. So to represent that, we're going to show an arrow pointing in to our ice cube. The heat is being absorbed by the ice. Mathematically, we can actually find out how much energy is absorbed. We can use our equation Q, heat, is equal to mass times our heat of fusion for that particular substance. For that particular substance, we have an unknown Q. We know that we have 235 grams of water, and the heat of fusion of water is provided in the question for us, 334 joules for every gram of water. So when we multiply that through, we are going to have 78,500 joules absorbed. It's important to include that word here because it's telling us the direction of our heat flow. And that is how you do a heat of fusion example problem.